Okay, this is lecture 20 on invariant maximality derivations by Harvey Friedman. Please.
Thank you. Um, all right, so we didn't quite finish last lecture. How do I use subtle cardinals to prove the full usability of the basic function? So we're gonna finish that, and I'm careful to figure out. I've set this up to be careful about which level of subtle cardinal is used to do what. That's actually responsible for some more complexity in this whole development. Uh, I'm planning to do all the way through 3.9 uh, in a few days, formal manuscript. More than 3.8, 3.9. Um, the next week, well, actually, next week we'll postpone the lecture because I have another engagement. But the lecture 21 is correct. Yeah, lecture 21 will start uh, with a greatly expanding section 3.7 on almost identities. We seem to be close to giving a simple, complete characterization of the usability of the almost identities, and this would uh, be far better than I expected. I just thought I was going to get partial results because there was a real block. But I think that I might be able to see my way through this. If not, then there's all kinds of partial results here. Uh, See, these particular functions we're looking at that and the ones that were reversed, are very pretty little ones like the identity on -1 to 0, followed by reciprocals, 1/n, 0/n, sorry, 1/n, 2/n, dot, 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 n/n. Uh, those uh, are the ones uh, that we're doing last lecture, and we'll finish up this lecture. But those are special cases of what's called an almost identity. An almost identity is just a function which moves at most finely many points. So it's an identity function plus a finite function. An almost identity is a function that just moves finely many points. And it would be far better than I was expecting if this goes through. In fact, if this goes through, the same characterization I use for the finite functions actually uh, holds the exact same conditions, hold for these almost identities to be usable. And this would be very satisfying. Um, Let me just move this over just a second here. Yeah. Um, I think it would propel the subject into a new level when you have such a striking characterizations. If this works, this would say that I can use RCA naught or less to completely understand the finite functions that are usable. But if you want to understand in the same way, the same conditions, the almost identities are usable, then you're required to use large cardinals. Yeah, that would be a very nice uh, formulation. Again, there'll be partial results if that doesn't work. I mean, there's already partial results. We're doing them now, but there'd be more partial results. All right, so reminding you that this is chapter 3 of this book, which I haven't changed the names of the title of the chapters. 1 is not done, really. That has to be carefully done. 2 has been done some time ago, although it stands to be perfected some. Is straight core mathematics about semi-algebraic and semi-linear, semi-piecewise linear functions on the reals, with concepts of invariance that are exactly like what we're doing for the real stuff, which is the rest of the book. Um, this is what we're doing now. This is all the positive stuff. This turned out to be quite a long chapter, actually comparable in length at least to this one, which was already pretty long. So we've done four, three we're doing. Five and six are serious additions to what we're talking about. Um, uh, yeah. Okay. So this is making it explicitly pi 0, 1. Uh, and there's an estimate. There's an estimate on called what is it called? Height of a rational number. So you basically, if you use height, the lesson here is going to be that one way of looking at the subject of invariant maximality is, in a way, if you bring in heights, you can get rid of you can make it explicitly pi 0, 1. The question is, how well a job do I do with that? And I think we'll be pleasantly surprised what I do with that. This is game theory, which is a well-known way of killing quantifiers and quantifier alternations. So this turned out to be well worth it. All right. So this chapter has gone through the early parts of this chapter are totally unchanged. It was all very stable through section 3.6, where I deal with I give a complete characterization of the finite functions that are usable. And this is a pretty, very intricate, very detailed section. And all of that can be done in these weak systems. There is something new that I added here. I don't want to spend any serious amount of time on this, but one corollary is that a finite function is usable if and only if every restriction of cardinal if and only if every two-element restriction is usable. A finite function is usable if and only if every two-element restriction is usable. In other words, restriction is a two-element subset of its domain. I thought that's pretty cute. And then if my new work works, an almost identity is usable if and only if every two-element restriction is usable. That this is actually true for almost identities, and of course that it's also equivalent to con SRP. All right, I'm not ready to quite claim that yet. That will be clear the next lecture. Next lecture, I hope to just be proving that. All right. All right. And I beefed up this chapter on the almost identities. So I have a lot more material on the almost identities. Believe it or not, there's a notion of there's a lot of intricate stuff, that has nothing to do with large cardinals about almost identities. What is the structure of an almost identity function on the rational interval -1, 1, which we use for everything? And it turns out that there's a lot of combinatorial trickery to understand that well. There's the notion of complete almost identity, and a complete almost identity has to be very concrete. A complete almost identity has to be order theoretic. A complete almost identity, and there's only countably many. A complete almost identity has to have domain, a finite union of what I call general rational intervals. General rational interval just means an interval with rational endpoints, which is allowed to be empty or degenerate. All right, so we're finishing up this main section. This is this powerful section where I do a lot of I do everything just involved. This is a very, very special, beautiful almost identity. Obviously, it's an almost identity. Only finally many things are being moved. 0 divided by n to n over n. right? Um, and this is where a lot of uh, set theoretic uh, a lot of set theoretic power, various set theoretic power, depending upon the size of n, what n is, and how much usability are we talking about? Are we talking about 2 usability or k usability? That means the dimension. And you see that I actually get some estimates here. By the way, there are no reversals here except the full one. Yeah. This one here is reversed. This is reversed. I haven't gotten into reversing weaker things, which is extremely important. This is some of the things I leave for to make the subject still keep the subject very much alive. Um, I'm expecting a breakthrough with this, by the way. The breakthrough I'm expecting with this is, and this here, is that whenever I use omega 1, I'm actually, in the proofs, I'm actually using more than Z2. I'm using more than Z2. But I believe that uh, I believe that that's not the best. In other words, this being K usable, this little guy being K usable is provable uh, in Z2. I think there's a hierarchy below Z2 that's developing. But that I'm not ready to claim yet. I have to get some time to do that. That'll be one of the things we'll do somewhat later when I talk about refinements. All right. So then we have what are these proofs of usability really? What are the formal systems really? See, because this is all semi-formal stuff. Semi-formal stuff. I say I use this. I'm not completely I'm not concerned with exact meta theory here. Actually, ZF minus power set is more than good enough for this. And I will, I quote that, but basically this is all semi-formal. And then I get more explicit about what exactly where are these proofs actually being conducted. There's nothing terribly surprising here. And then finally, I can actually use con statements. I can use con statements to prove these things instead of actual set theoretic assumptions. You can use con statements. All right. And now this is the section that remains to be done, that I want. I don't, I'm not claiming this today, but this is the plan. I build this up to this. Okay, and that's characterized the same way that the finite functions are, if this holds up. Uh, and then we want to finish with refinements. This probably is the last you'll see of this chapter. We have to do this bookkeeping statement. Remember, we reversed a statement that had k equals n in it. If you remember that whole reversal, the dimension and the number of indiscernibles were the same for convenience. And how do you know that that is actually the full statement with arbitrary k and arbitrary n? And that's a nice, you know, elementary thing. So we end with that. Uh, okay, so let's start this. So this is fully K usable using, uh, yeah. So one subtle kicks in at dimension 3 if I have n equals 2. So this is saying that the weakest form of all this is k equals 3, dimension 3, and n equals 2. And then I need a one subtle cardinal or so-called subtle cardinal. Uh, we don't know that this is best possible. This feels best possible. It's best possible with the standard proof ideas I'm using, right? I mean, it feels like it should be, but those are all these reversal issues that I don't touch in this book, not book one at least. I'll see how people do with this reversal stuff, whether they need my help or not. Um, all right. So there's an appendix A on these large cardinals, and it's based on an old paper of mine called Subtle Cardinals and Linear Orderings, where I develop all this level of the large cardinal hierarchy, and there's a lot of information in that paper. And then there's an appendix A in this book, uh, which summarizes the high points uh, and definitions. So we know what an unbounded subset of a limit ordinal is. We know what a closed set is. This is the set of all subsets. This is the set of all k-element subsets. A regressive function, we know what that means. F of x is contained in min of x, because we're doing von Neumann ordinals. This makes sense. Now, homogeneity, F homogeneous, means if I have two a B and C in SKE, we have F of B intersect min of B union C equals F of C. So it means that F of B and F of C agree on their lower they agree on the lower part. See how that works. So these are the official definitions. By the way, James Baumgartner, who died tragically early, um, was the main, not the only, mover of this theory of this level of the hierarchy. And a lot of the stuff I do in that paper is stuff of his, which I rework, and maybe some refinements. It's definitely some refinements here and there. But then I go to linear orderings. There's a number of things I do in there that are new. Like weaker forms of the large cardinals are the same as the original forms, stuff like that. And also what this hierarchy means on linearly ordered sets. Okay, but that's the background material. Uh, so the main definition is lambda is k subtle if and only if, and k is greater or equal to 1. K lambda is k subtle if and only if for all closed unbounded sets C and regressive functions from the k element sets into the subsets. There's an F homogeneous set A of cardinality k plus 1 inside the closed set C. So the k element subsets, there's only k plus 1 k element subsets of a k plus 1 element set. And the idea is that all those could cohere on their values. So that turns out to be the right definition, or Baumgartner definition, if I remember right. So I need to massage this in order to use it. So oh no, this is an extension. Yeah, I think I credit this to Baumgartner. Yeah, yeah, I think I credit this to Baumgartner. It's not obvious, but it's proved in that paper from scratch, and I think it's due to him. That there's an F homogeneous set of every cardinality, not just of cardinality k plus 1, but you actually get a one of every cardinality less than the k subtle cardinal. Yeah. Actually, I only use this. I only use this in this work we're talking about. I only use this to get an infinite F homogeneous set. Not. I don't need it so big. Turns out. All right. So in my setup, I have k subtle limit ordinals, but k subtle cardinals are much more common to read than k subtle ordinals. But it doesn't make any difference because if alpha is not a cardinal, there's a closed unbounded set C. That should be inclusion sign. There's a closed unbounded set C uh, contained in the ordinal of cardinality smaller than the minimum of C. uh, whose cardinality is smaller than its minimum. And from that, you can get the K-subtle ordinals are automatic ordinals or must be automatically cardinals. Because if it's not, then you get something where you can ruin the subtlety, ruin the K-subtlety. So K-subtle cardinals are the same as K-subtle ordinals. All right. We need to put K-subtlety of kappa into a form we can use directly for usability. Um, so if I have a K minus 2 subtle cardinal and I have several functions of arity, various arities less than or equal to K minus 2, which are regressive, and I have a closed and unbounded set C, then I can find an infinite set. Here, you see, I only need infinite. An infinite, I can get one of any cardinality less than kappa, but that's not important, as I told you. There's an infinite set V, which is like indiscernibles, meaning for any order equivalent X and Y in there, um, and for any one of the functions, we have the coherence. Yeah. So this just generalizes it to finally many regressive functions with any number of arities. This is the original definition, right? It's just for every one of these functions and for every arity. These functions can have different arity. Uh, these are a little tricky to prove. I mean, they're not tricky to prove, they're tricky to write down correct proofs of, with some details. But next one is harder to write down. All right. Uh, I call C and D kappa good, and I need to have the dimension K we're talking about. If C is a subset of kappa, is closed unbounded, and D is any set, then the following holds. Namely, that I can push up an indiscernible by one. So if I have a finite sequence and I raise all copies of its max to a greater element of C, and its max happens to be in C, sorry, its max happens to be in C, uh, 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 then if I raise all copies of the max to a greater element of C, I don't change its membership in D. So that's what CD is kappa good means. Kappa good K means. It's the kind of indiscernibility we want, but just for moving the top point, the top coordinate. It turns out in invariant maximality, the way we go about things, this comes for free. This comes for free, but the general combinatorics, it's not for free at all. I'm talking about general combinatorics right now. Now, um, if D is order invariant, D is said to be order invariant lower, order invariant lower. I changed this to lower order invariant. I didn't do it everywhere. Lower order invariant. If and only if, whenever are in V union alpha to the K, where alpha is in V, they're order equivalent, then you have whenever they're equal and they're equal below alpha. They're equal below alpha. So above alpha, they have to be in V, right? And alpha is in V. Then they're actually uh, we have equivalence. So this is a kind of indiscernibility, relative to parameters below, right? And then the lemma that we need. Now, remember, I'm trying to actually get numbers that are dimensions that are accurate, numbers that are accurate, and this is why this gets a little tricky. So let K be greater than or equal to 3, and kappa is a K minus 2 subtle cardinal, and CD is kappa good slash K. There exists an infinite set V such that D is lower order invariant. Yeah, I think I changed this. Lower order invariant over V. Yeah, and this takes a little work. You see, you want to make sure that you use no more than K minus two subtle. See. Um, but you need CD to be, if I didn't have this hypothesis, this would be much simpler to write down the proof, but also the result would be that I would need that it was K minus one subtle. You see, I would need that it was K minus one subtle if I didn't have that hypothesis. See, all right. Now we have to actually change the combinatorics to this space for technical reasons. And it's really nothing to really waste our time talking about much. Okay. Um, yeah. So we just have we just pairing the things in V are paired with zero. Uh, and it's really the same statement. So eventually we get now we want to tear this down into its bare bones. So eventually we get this. Now I don't know if you remember from this last lecture or a couple, even the last couple of lectures. There's this thing called W sub kappa that comes from this elementary substructure tower stuff. Uh, uh, that's a particular closed unbounded set W sub kappa. And we pick a set of type omega such that the following holds. If let E be order invariant, uh, and I have these pairs, these P's are innocent rationals, uh, then I get this. This is what I'm looking for, this equivalence. Because if you remember what S sub E kappa was, it's the this is the greedy construction based on the order invariant E. This is the greedy construction. All right. Uh, yeah, this is a space. This is the space corresponding to this cardinal, this ordinal, indiscernible. This is the space. All right. Okay. Remember, this is invariant maximality. Everything is invariant maximality. That's what we're looking at. So from this, you actually get what we want. Uh, okay. This should be the Greek letter kappa. Let's not worry about that. Okay, that's what we're trying to do. And then actually, I'm able to do something a little different, maybe in some sense stronger. What happens when n is much smaller than k? What happens when n is smaller than k? When n is smaller than k, you can get away with an n minus one subtle cardinal. Uh, so I have to rework everything where where I don't where I use fewer indiscernibles. See, fewer indiscernibles. I don't know why this happened. Why I got misnumbered. Oh, I know why I got No, no, no. I don't know why this is misnumbered. I have to renumber. Um, okay, so I've actually reworked the whole thing when n is less than k. I mean, when n is less than k, I can use k, but now when n, I want to take advantage of the fact that n is smaller, I have to do some more work. It has to be done just right to make sure the numbers match up right. Okay. Um, Yeah, this is, remember, this is this K, this, yeah. So that's like it was before, except before it was, this was K and this was K minus two, whatever. It was different. Uh, we're just repeating what we did before. It just all looks the same except slightly different. Um, I think I don't use the star anymore. And then finally we get this. That if n is greater than or equal to 2, and there's an n minus 1 subtle cardinal, then I don't care what k is. And then you can put these two together. You see, then you put these two together, you trivially get this. This is a trivial step. Then you can use min k minus 2, n minus 1. So you have the best of both worlds. You take care of both cases in one fell swoop like this. All right. So now that was sort of something that I was talking about last time, but we didn't finish. Okay. Um, by the way, I am going to, this became more complicated than it needs to be if you want cruder results. So I think that I will have some user-friendly things in this chapter. What is the simplest argument with the least details that does with large cardinals with the result, even if I don't have the subtle cardinals, the how much level of subtle cardinals I'm needing, even if I don't have that optimal at all. What is the simplest argument? So there will be a thing in there like that. So readers can go like that and not even look at these things that are more intricate, that I have to argue more carefully. And I definitely want to do that. And I'm also going to do that for using omega 1, for the little stuff. I'm going to definitely have that because I spent a lot of time trying to get conjecture to be optimal things here. And that makes it more complicated. So I definitely will do that, streamline to get uh, the clearest possible arguments for the things. What can you do in Z2? What can you do in Z? And what can you do in SRP? I don't know much about what you can do between Z and SRP. I think there's nothing in here like that at this point. To hit ZFC, but that's something else. We'll talk about that later because it just occurred to me that there's going to be something in this chapter that I haven't told you is going to be in this chapter. So let's not worry about that right now. All right. So the rest of this stuff here is about how do you make these formula? How do these proofs work? What formal axioms am I actually really using? All right, so ZFCF minus power set plus omega 1 exists is enough for this stuff. And that's done by inspection. So if you actually literally say, what did I really use in these semi-formal arguments? Uh, it was ZF minus power set. You can actually check that. Um, okay, so and then what do I use to do those? Because we did those first, before before today. Today we did this. But what did I use? Well, you can actually show that that Z is enough. Uh, the ZF minus power set uh, is needed. There's some infrastructure here that's sort of immediate if you're in Z. Uh, but the infrastructure, you might as well just say Z here because Z is going to be needed anyways for these arguments. Because power set enters in here, in the proofs, iterated power set. Excuse me, I should say this. Erdős-Radó is in here. So Z is the natural place for this. Um, SRP plus is the stuff we just did. That's the natural, obvious place because these subtle cardinals are part of SRPs. They're weaker than the stationary Ramsey property. They're immediate consequences. All right, maybe not immediate, but they're consequences. Yeah. So now, how do we get uh, better bounds, better formal systems? So first of all, for this system, ZF minus parsec plus omega 1, for arithmetic sentences, that's conservative over Z3. Um, and yeah, and then there's no largest infinite von Neumann order in Z prove the same arithmetic sentences. So it turns out uh, this is enough to do the semi-formal arguments, and that's why Z is enough. Yeah. All right. So we wind up with this result that I only need Z3 to do these. Now, I actually, as I told you, earlier, I think that I can improve on this nicely. That if you fix the dimension in here, if you fix the dimension in here, then I think Z2 might be is enough, which is a much better result. And that suggests a hierarchy, and that's very interesting. Uh, and here, if you fix N, I feel like Z2 should be enough for that too. And my idea for proving this is very cute and interesting, but we can't talk about it today. I have to check that it works also. Yeah. But my feeling is Z2 is enough for N fixed here, and Z2 is enough for this here with the usability dimension fixed. All right. Now, here, Zermelo is enough to do these things, and a finite amount of type theory is enough when N is fixed. Uh, when you fix the dimension or the K, you can get this. All right, this is just what we did. That doesn't require any real comment. But now we get some more specific information. Uh, uh, so I'm claiming that you can use con statements. So con Z3 is enough to prove this stuff. That's not surprising because these are pi01 statements. So there's some general nonsense about if you can prove some pi01 statement from something, you can prove it from con of it. Right? You know, this is how I do that. You need WK naught in the background to know the things are pi01, because they're only implicitly pi01. Yeah, so con SRP is enough to prove this. Fully usable. All right. Now, in here, in this stuff, uh, I go further. There are two parameters, K and N here, implicit parameters, K and N. Of course, you can quantify, the official statements are quantifying over all K and all N, right? But there are two key parameters. One is the dimension. So you have an order invariant relation. What dimension is it? And the other is the so-called number of indiscernibles, N. And uh, and you can fix both K and N, and you get a statement, which is pi01, which is you get an actual statement. And and here are three shapes, right? These have this gaps in them. Okay. And I calculate what my proofs give in terms of what do I need? What do I need to prove this? What do I need to prove this? What do I need to prove this? Where the K and N are fixed. Okay. This is rather complete treatment of this. Okay. Um, Now here I only fix N and I have K quantified. And that's what fully usable means. If you remember what fully usable means, it means your K usable for every K, where you quantify over the dimension. You quantify over the dimension. So fixes the number of inassertables and allows the dimension to be universally quantified. Same thing here with these three different shapes. I mean, this being the really powerful one, no gaps. These two have gaps. I mean, the long story short is that this is like fragments of Z, and this is like fragments of SRP, so to speak. All right. Now we do it the other way. We fix K, and just look at K usable, that is dimension K. We fix K and we quantify over the number of indiscernibles, all n, right? We also get the same kind of phenomena. This stuff being in Z, fragments of Z, and this one being fragments of SRP. Yeah. All right. And then finally, we quantify over both at once for all K and for all N. And a systematic treatment, this is what we should be doing, and then we should see what we get, right? And we work this out. Need some obvious definitions. What is nth order arithmetic? We need to know that. So when K is fixed, we treat these as I said, and I don't have too much time. I don't want to just dwell on this. There's always this trivial stuff when K is 1 or N is 1, whatever. Those are all handled in RCA naught by previous stuff in this chapter that we talked about. So here's what happens when K and N are fixed. We need Erdős-Radó comes in, and we just need min of K minus 2 and N minus 2, that many iterations of omega with a power of 2 function, 2 to the 2 to the 2 to the 2. And then you have to put a plus on top. If you remember, Erdős-Radó has like that. All right. But that just tells me what cardinal I need over ZF minus power set. That's not quite what we want as a proof theorist. We'd rather have this, right? So this is what you get by some conservative extension, some trickery. You get this, that you actually it's min K plus 1, N plus 1 order arithmetic. That's what you need when K and N are fixed. It's that level of order of arithmetic. And the baby cases are the real baby case is this, but the baby case is this one, and Z3 is enough, right? Because I know how to calculate min of K plus 1, N plus 1 when K equals 2 or N equals 1. Yeah, all right. So, okay, but it looks like I'm getting Z2, but I'm actually getting something lower if I actually let N equals 1. So this is certainly a true statement. When N is 1, the result is better. When N is 1, it's nothing. It's provable trivially. Okay, maybe a little confusing. All right, and then finally we get this. So that's what the subtle cardinal level is needed. And I just throw in ZFC gratuitously here. A more refined thing would have less. But since we're dealing with large cardinals anyways, throwing ZFC around isn't such a bad idea. So I just do that, even though this can be reduced. Okay, and then I have this one giant statement that includes everything I said. Okay. And now we go from K fixed and N quantified. Yeah, K fixed and N quantified, and we get similar phenomena. Let's see. If K is fixed and N is quantified, we get with K is 1, it's RCA naught. K is 2, it's Z3, and K is 3 and higher, it's subtle cardinal of uh, rank or whatever level, K minus 2. And then what happens when we uh, yeah, we get a consolidation of everything I said this way. When K is quantified, N is fixed. Similar phenomena. Let's see where we go here. N is fixed. We're going to use N plus first order arithmetic when N is greater than or equal to 2. When N is 1, there's nothing. If you look at what I'm doing, when N is 1, there's nothing to prove. Uh, okay. Why do I say that? When N is 1, maybe there is something to prove. Yeah. Oh yeah. Okay. Sorry. So I've been saying some things that are inaccurate. Yeah. This is the case when I have 0 divided by 1, comma 1 divided by 1. And that definitely needs Z3. Well, Z3 is the appropriate thing for that here. But this looks like this is inconsistent with each other, so I must have copied something wrong. All right, I'll fix this. This is bookkeeping. Uh, yeah, so I obviously screwed something up here. This is an yeah. Let's see what. Oh, I know what happened. C3. No, where was the one that screwed us? Where's the one that I just a sec. Yeah, between these two, which one is the RCA naught? C3. Okay, C3 with N equals 1. What is going on? C3 with N equals 1. 0, comma 1. Fully realizable. But that needs Z3. Yeah. I think this is what I meant. Yeah. Yeah, that's it. Because when N equals 1, this is trivial. So this is a typo. Yeah. That's all right. We're still on track. Okay. Now, when K and N are both quantified, when K and N are both quantified, uh, we get from just the reading the informal argument, we get this. And this. Yeah, for every M subtle of M. Yeah, subtle of M is a theory that says there's an M subtle cardinal. Yeah. So this is the best way to say this is D1, D2 approval in Z. So you can't cut it back because these are universally quantified, the parameters are. and then D3 would just be this. So this is the right way. This is what you get. But it's harder when you start fixing stuff and letting some stuff vary and other stuff fixed. And I found it worth doing. I mean, I like a lot of pain, I see the thrive on pain. So that's why I did that. All right. Then you can prove everything with cons. So I have a bunch of stuff here about how you can prove stuff with con. Uh, all just what you'd expect with con. And that requires implicit pi zero oneness. Yeah, here. The way you get this by showing that if phi is provable in T, then phi is provable with con T under a suitable hypothesis. If phi is implicitly pi zero one over WKL naught, and T is special, special doesn't means it's not very special. It just means it's a decent formal system, a decent for adequate formal system. Um, then if phi is provable in T, then phi is provable in WKL naught plus con T. And then you just simply transcribe everything. All right. So I have a couple more minutes, a little more. So I didn't think I would get to 3.7 very much, but I have a couple, a little bit. And this is the rework section because we had an earlier form which had essentially no content. This is a lot of information about the almost identities. So an almost identity is a function which moves at most finely many points. And we just get clear about what does the word rational interval mean and all that stuff. There are continually many, but a basic one is one where the domain is a finite union of general rational intervals, and they turn out to be important. But we can handle arbitrary ones. It turns out the fact there are continually many turns out not to be a problem at all. But the ones we really, of course, care about most are the basic ones. Those are the concrete ones. Or they're actually the same as the order theoretic ones. So that's the same as the order theoretic. Now remember, strictly increasing is an overriding, everywhere present, necessary condition in this whole subject. We only care about strictly increasing functions because the rest of them are not usable, except in dimension one. And dimension one is a simple, crazy little subject of no special importance that we took care of a long time ago. One, usability, we understand completely. That's below the radar screen. Two, usability and higher is the only thing interesting. All right, so psi-al is a set of all strictly increasing almost identities. And psi-bal is a set of all strictly increasing basic ones. All right. And now we define a notion of completeness. I don't want to go too much farther here, but there's a notion of completeness, and I absolutely characterize all the complete ones. I characterize completely all the complete ones. They have a nice shape, make you feel real comfortable. Actually, here's the shape. Here actually have a nice cube. Here are the shapes. And these shapes are going to be important because we're going to show that everything is usable here except with one obstruction. I hope to show that. That's the thing that I'm in the middle of trying to make sure is right. Okay, and these are the complete ones. All right. Okay. I think that I'm done because it's 1 minute after 11.